Hello. We are going to in this video we are going to study what is the optimal weighting matrix and how to implement the optimal weighting matrix estimator. So first of all, we discussed like the choice of weighting matrix is important, but no matter what you choose, your estimator is not wrong, because suppose that you need to estimate, say, two parameters, but you have 5 moment restrictions. So you have 5 but only need 2. So then, as long as the model is correctly specified, as long as all the 5 moment conditions are correct, you can choose any 2 of them. So there are 5, just choose whatever 2, like this or like this or like this. Whatever you do, always you're correct. So because all of them are correct assumptions, so just you need only 2. So take whatever you need, just choose whatever you like, then your estimator will be consistent. So what I'm saying by correct is that your estimator will be consistent. However, as you can expect, first, using 5 moment conditions will be better than using 2 conditions, because in terms of the amount of the information, so you are using more information by using all 5 assumptions than choosing 2 of them. That's the first difference. And second difference, among these 5 moment conditions, some moment conditions may be more informative, provide more information, or maybe more helpful, or easier to handle, or will have less noise. So simply, like, some are more informative than the others. In that case, putting more weights on more informative moment condition helps your estimation, like helps the efficiency, improves the efficiency of your estimator. So because of these 2 reasons, like choosing the weight, so your estimator will be always consistent. However, if you can efficiently use those assumptions, your estimator will be more accurate and will have smaller variance. So making the variance smaller is the goal in this video. So by choosing the optimal weighting matrix, and that is the basic motivation of considering this issue. And then, first of all, however, the problem here is you have 2 parameters, say, and then the asymptotic variance must be a 2x2 matrix. 2x2 matrix. So if you use this weighting matrix, you get a 2x2 asymptotic variance matrix. And if you use a different weighting matrix, you are going to use another different 2x2 variance matrix, asymptotic variance matrix. Then, how can you compare 2x2 matrices? Which is larger? The answer is here. So now, when the variance is one-dimensional, comparison, the inequality is straightforward. The smaller the variance is, the better. But when they become matrices, covariance matrices, you have to use this definition for the inequality. So sometimes there may be no inequality holds between these 2 matrices. But if A minus B is another 2x2 matrix, if A minus B is strictly positive definite, then we say matrix A is greater than matrix B, right? It's an intuitive definition, interesting definition. However, as I said, A minus B may be neither positive definite nor negative definite. In that case, there is no inequality can be written in between A and B. So, however, in this theory, the first interesting result of this theory is that there exists optimal weighting matrix or optimal asymptotic variance that satisfies this inequality for any possible weighting matrix. So if you choose this weighting matrix, then always that matrix will, the asymptotic variance will satisfy this condition, strict positive definite condition. So that's why I said, that's one of the reasons why I said the theory is beautiful, like interesting theory. And so then now we know how we set our objective. We would like to minimize the asymptotic variance matrix in this sense, by this definition. And remember, the variance matrix was this long formula, and we can choose W. The only thing we can handle in this formula is W. And spoiler, the answer is the optimal weighting matrix is omega inverse. Omega inverse is the ideal weighting matrix. And then think about omega inverse here, G prime omega inverse G. And G omega inverse omega inverse. So this will be cancelled out. Omega inverse omega will be cancelled out. So the middle term becomes G prime omega inverse G, which will be cancelled out by this. So there is another G prime omega inverse G. Here is another G, and that is taken inverse again. So this much is cancelled out, and in the end, the asymptotic variance simplifies to this guy. So this is another reason, second reason, why I said the theory is beautiful. So after considering a few more issues, the variance becomes simpler. So isn't it nice? The proof is complicated. Showing that this satisfies this condition is not easy. I'm not confident I can do it right now. I need to read textbooks, and I learned it before, but I'm not so sure. I'm not confident. Right. There is an interesting theory. When I was a PhD student at Yale, I was a TA. I was TA for a PhD chromatrics course, and a student asked me how to prove this. And I failed. I could not prove this for the student, and I searched for the paper about this, and what I find is I found a paper showing this proof, but the author was my classmate, my PhD classmate at Yale. He majored in mathematics before coming to the PhD program, and he had a short paper about this proof in a journal. So I was very much surprised by that. He's now a professor at UCSD. So I cannot prove this right now, but I can. Like, if you're interested, I may try later. And then let me explain what this means. So we have the result. I'm going to skip all the steps between here, the beginning to the end. So I only explain the beginning, and I jump to the end. So this is the end. And then look at the asymptotic variance here. You have capital G and omega. And we have the same intuition as I explained in the previous chapter. So the derivative, so remember so we are calculating, so I will open, let me open the one second, sorry about this. So we used this graph to show you the importance of variance. So it's obvious. So the variance appears again. Now, in the previous chapter, it was about the variance of L prime, the derivative of log likelihood function in MLE, but now omega is the variance of the moment function itself, right? The moment function itself becomes the variance, like is associated with the variance, and then now the derivative. Think about the derivative. The curvature, I explained it as a curvature, and the curvature depends on the second derivative of the log likelihood function. But now, so remember, the variance was about the first derivative, and the curvature was about the second derivative. But in the GMM, the variance was about G itself, moment function itself, and the curvature is replaced by the first derivative. So you have to reduce the order of the derivative by 1 when you compare the theory from the previous chapter to this one. So G is the slope of the moment condition. So think about, I will prepare some graphic devices and we'll continue. We'll give you the intuition in the next video. Thanks for watching.